Welcome everyone. In this lesson, we're going to see how to find and classify our local extreme points. And it comes down to, well, something we've already been doing, finding the critical numbers of our function. So we know that involves the derivative. We'll kind of review over that. But then really the new material is once we have our critical numbers, we want to be able to classify them as either a local max, local min, or neither. And so we're going to see two tests on how we can classify them. There's the first derivative test. So we can use our first derivative to help us classify whether a critical number is a local max or local min. Or there's the second derivative test. That can also be used. So we're going to look at both tests. But first, let's just kind of start by reviewing over how do we find these critical numbers and why are they so important? Why do they have that name, critical number? All right, so finding local extrema. There's a really nice theorem here that kind of points us in the direction. How do we actually locate, given a function, how do we actually locate where the high points and the low points occur? And this is Fairmonts Theorem. And let's read through it. We've seen this one before, but let's read through it again. It says if function f has a local maximum or local minimum at some location x equals c, then one of two things happens. Either the derivative at x equals c is 0, or the derivative there is undefined. So really, this gives us a place to look. This gives us we want to look for where our derivative is either 0 or where our derivative is undefined. And because those two types of places are so important, we give them a special name, and we called those the critical numbers. So the number x equals c is a critical number of function f, provided either the derivative of f is 0 there, or the derivative is undefined there, with one extra condition, that the critical number c has to be in the domain of our original function. So that's something we want to kind of pay attention to. We are always interested in where the derivative is 0 and where the derivative is undefined. We saw that with intervals of increase, decrease. And when we're talking about the second derivative, we were interested in where the second derivative was 0 and undefined. But in terms of critical numbers, in terms of locating maxes and mins, we want this extra requirement that x equals c has to be in the domain of our function. So it's kind of a subtle point, but it's important. So x equals c, if it's going to be a critical number, not only it has to meet one of these two requirements, but there's also this additional requirement that we want to keep in mind. So this is just kind of a thing to just to remember. All right, so let's see why. Why does, what are some examples of Fairmonts theorem here? And so we have this first graph, and we see what we're seeing at x equals c is this is a local minimum. If we look at this graph, this is a low point right in here. And, there might be other points if we go further out along our curve. There might be other low points, but right in this little area, in this little neighborhood of x equals c, we can find some interval surrounding this. Right in this little interval here, that's as low as our function gets. And what we're seeing here is at this low point, it flattens out. The graph flattens out. We have a horizontal tangent line. So this is an example of what it would look like if we have a local min and the derivative is 0. Well, in the second graph here, we have a local min. Same kind of thing. We look in a little neighborhood of that point, and there might be other low points out there somewhere else on our graph, but right around this point right here at x equals c, that's as low as our function gets. Right in this little section here, that's as low as our function gets. So that's another example of a function that has a local min at x equals c. But in this case, we're seeing what happens when the derivative is undefined. Why is the derivative undefined here? Well, we have a cusp. There's an abrupt change in the slope of our graph. The derivative is 0 here because it's more of a gradual, it's more of a rounded change in the slope. Here it's much more drastic. All right, so in both of these graphs, we see an example of a local min where either the derivative is 0 or the derivative is undefined at x equals c. So this kind of gives us a strategy. How do we actually find the local extrema? Well, we're really interested in where the derivative is 0 and where it's undefined. So that's going to be the first thing. First thing we look for is find the critical numbers. Now, that's only the first step. And the reason why it's only the first step is because there are critical numbers that are neither a max nor a min. And that's what we're seeing over here in this third graph. So here, it's not a max, and it's not a min either. But in this example, the derivative is 0. So the graph flattens out. So the graph does flatten out here. There is a horizontal tangent line. But if we look a little bit to the right, the graph goes up. And if we look a little bit to the left, the graph goes down. So this point at x equals c, it's not really a max, and it's not really a min. There's points that are higher, then there's points that are lower if you go in either direction, or slightly in either direction. So if we even just look in a little section surrounding this point, it's not a min because I can go lower if I move to the left, and this isn't a max because if I go a little bit to the right, my function starts getting a little bit higher. So this is not a max or a min. But it is a critical number. This would be a critical number because apparently x equals c is in the domain of our function and the derivative is 0 there. So these critical numbers, it's not the end of the story. So the critical numbers, there I go, trying to write in a highlighter again. The critical numbers are only possible locations of extreme points. So the key word there is possible. So the critical numbers are only possible locations. Might be a min, might be a max, it might be neither. And we have to do an additional step. So the additional step, this is where we're going to see how to classify the critical numbers. So a lot of times we call this testing them or classifying them. And we have a few options on how to do this. We're going to see the first derivative test and the second derivative test. We can use either one. Sometimes we might want to use one or the other, but we have some options. All right, so this is the little strategy we're going to use to help us find the local extreme points on our graph. We're going to find the critical numbers. So that kind of narrows our focus down. That gives us the possible locations where we're going to have a max or a min. And then in the second step, we're actually going to use a test to determine, okay, is this a max? Is it a min? Or is it neither? All right, so just a quick review. Well, maybe not so much quick, but a review over how do we find or how do we locate possible locations where we have a max or a min, and that's the critical numbers. So we'll look at the first derivative test next.